In this particular computer video, we're going to look at a cluster of galaxies called AbellS1063, where there's an active radio emitting halo along with some point sources in the cluster. And AbellS1063 was one of the sources selected from the Hubble telescope for looking at lensing, gravitational lensing effects, and what they tell us about matter, etc., inside large clusters of galaxies. So we're first going to look at a background image from the Meerkat Cosmos survey. And the Cosmos survey was essentially stitching together about 8 or 9 separate fields, covering about 2 or 3 to 2.5 degrees or something. And this was observed by Ian Haywood and colleagues, and this image is taken from their, I think, 2022 paper. There's quite a number of interesting objects in this field. Here's a giant radio galaxy, and there's another one down there. We're actually going to be more interested in this area, and there's a little marker here of a head-tail galaxy moving toward the central part of the cluster. And the following image is going to zoom in on this area in more detail. And here we are. So this is our little cluster head-tail source, which we saw recently back in the previous image. With a little adjustment of the scaling, intensity scaling, etc., we can see there's quite a number of interesting radio sources in the field. This, when you do an optical identification, is a head-tail galaxy moving through the cluster. This guy seems to be moving in toward the cluster center, and there's also another kind of broad, very broad head-tail galaxy also with wings behind it moving presumably toward the center of the cluster. And we can actually see here in the middle there is actually diffuse emission, and we'll see that it's actually, when we do some image processing, this comes out to be quite large. The main central big lensing giant elliptical galaxy in the cluster has a couple of Millijansky point sources, which is this image right here. And nearby there's, in this particular example, there's a spiral galaxy. This is actually a lensed image of a spiral galaxy, which presumably actually lies behind in the large central elliptical galaxy. So what do we want to, we first of all really want to sort of try and dig out the diffuse emission here, and when we can separate out that, we want to get point source values for these particular images in the cluster. So we're going to go through this example script, which is included in the distribution itself, and kind of like the previous image with 3C previous study with 3C236, we have to have a .csv file which contains a sort of a standardized name of the source. And since we want to do some cosmology with this thing as well, it contains information about the in the .csv file, we contain information also about the redshift and, where we know it, the spectral index. So when we're doing processing with, here we have, for example, this AbellS1063 CSV field. We can actually look at that. AbellS1063. So here we have this standardized image, AbellS1063 RA and DEC. Sort of a search area, and sort of redshift of 0.351, and the spectral index is minus 0.8. This 12 arc minute, I can't remember, secondary, is just sort of a search area, angular size area for looking at sources if we don't know where it is. Okay, so this is occasionally consulted in the background. And what we first want to do is figure out, we want to try and separate out the point sources from the diffuse emission by mathematical morphology, again following along the lines we were looking at with 3C236. So in the case of 3C236, we found that we got a very good result with just doing a single erosion followed by a single dilation. And when we try and do that here, we're going to get the following. Let's see if let's make sure we got these things up to date. And then we're going to get this particular function call here says that we're not going to, double erosion is set to false. So we're only going to get a single erosion. We're going to get this particular image here. And let's see what that looks like. And when we expand that, we find that there's kind of leftover artifacts in the single erosion. Here we didn't really get entirely remove the all the emission here. A lot of these sources have little sort of leftover artifacts, etc. here, and sort of got kind of little point source or little spikes sticking out of this thing. And so this image isn't really that useful for doing doing science. So we said here, okay, let's actually do a double erosion. So we do have two erosions followed by a single dilations, and this is done in the following thing. Here, since double erosion is false, we don't have to have that stuff. And we'll do this. So, let's see, didn't we get there? Oh, oopsies. GH 6 times the RMS noise. And we're doing double erosion. And double erosion actually is the equivalent of taking the original erosion size and then doubling it in size. So you don't need to do erosion twice, but you can just do it with a single erosion, which is dimensionally on each side twice what the single erosion is. So if we look at this, we can see actually we've sort of got much cleaner removal of these bright sources, etc. Now, I know in advance already that my halo is not going to get much bigger than this area, so we might as well add these two infalling head-tail galaxies back into the image by selecting from the removing them from the compact source list and adding them back into the main image. So let's go do that. Now, what we also found, if we look at if we looked at that particular image, we would see that there's actually going to be some holes left behind in the main image, and so we can actually fill those in with what are called Navier-Stokes inpainting. Well, first of all, we're going to again have to modify things due to our cluster galaxies thing. Let's see here. So we're going to remove the AbellS1063 fits file. We're going to then link the final image our 10 standardized field. And then we're now going to do something called in-painting. In-painting allows us to fill in the holes in our image by what's called Navier-Stokes in-painting. Navier-Stokes, as some of you will recognize, is kind of describes fluid flow, so that if we have a hole in an image, we can compute to Navier-Stokes what would happen if the emission from the surrounding the hole flowed into the area covered by the hole. And what we can do is, so we have an in-painter function, which we will call, and the in-painting result is something called, for fast Navier-Stokes in-painting, we use the Open Computer Vision task, which is generally much faster. Navier-Stokes things requires you to solve equations, and one of Python's non-strengths is it's not very fast at solving equations generally. So if you can, you'd like to use a faster image in-painting program, which we happen to have available to us here. So the in-painting result has generated this thing called Computer Vision Navier-Stokes in-painting result. So again, then we want to get the parameters of this unconvolved image. And we'll again do the logical thing here. And then we can get the galaxy parameters of the field, saying what the thing is. We're going to go down to a 3.5 times the theoretical noise. Dash S is false because we do not. That's an option to actually subtract off the flux of a central point source, which we don't want to do here. And dash U says we're not going to use super polygons the way we used back in the 3C236 observation, because we have three separate sources which we presume are not particularly related to each other. So let's say get galaxy parameters if false. So here's our initial look at what's going on here. Now we can see here there's kind of a faint area here where one of the point radio galaxies, the head-tail radio galaxies here has the area in this, for what we think is the cluster image, that's been filled in by Navier-Stokes in-painting, and we can actually just separately determine all the individual flux densities of these sources, 1, lobe 2, just that they're all going to come out separately. Let's see what that looks like. So again, here's our source redshift reported out. Now the median flux density is found by this Brisoro program is about 0.004 millijanskis, which is very close to what Ian Haywood and company were reporting in their 2022 paper. The initial flux density here is about 8.5 millijanskis with an error of about 0.5 millijanskis. There's all sorts of interesting diffuse emission here about the nominal apparently projected size, blah, 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 etc., and position angle of the lobe. And also then we have separate values for the source centroids of the other two objects. And the other two objects, we're actually assuming here that they're related to the cluster, and that the presumably the redshift is the same, so things like that are things about pretty well similar. Now what we want to do is actually, we still like to convolve, we want to convolve this image by to see if we can dig out some more flux out of this thing. Now let's see here, we can just remove we can do a convolve image of the AbellS1063 image we're going to convolve by a factor of 3. Now then we have to we can get the galaxy parameters for the convolved image by using a dash convolve factor equals true. So let's do that. So lo and behold, as we've convolved by a factor of 3, and you can see our convolved image is getting quite a bit larger. And let's just do we'll do our central lobe of the halo source halo diffuse emission, and that is going to produce a report like this. So we are now actually almost doubled our flux density up to about 16.8 millijanskis. So it's almost about double the size of what it was originally. So that we've actually dug out quite a bit of diffuse emission. Now, you have noticed in our original emission we did have 2 point sources in the couple of point sources that we want to determine the point source of the nucleus of the central giant elliptical galaxy, and we want to find out what we can about that. The other source in the field is that sort of lensed spiral galaxy, and so let's see, we can so we've now finished our diffuse emission, and now we want to actually go back and figure out what's happening with these point sources. So now we want to get the point sources. So we want to subtract off the in-painting results that filled in the image, and we have to use the mask which was generated for in-painting, and we have to remove that, since if we just sum the point sources individually, the areas of these point sources individually, now we get more flux for the point sources out than we actually fed in, since in-painting has been added. So what we do first is we have to do an image math where we take the in-painted result and we multiply that with an image math function which can add, subtract, multiply, divide, etc. We're going to do image math.pi. We want to multiply the white top hat mask by the in-painted image, and that'll give us a bunch of point sources all sitting on top of a bed of zeros. So let's just copy that and do that. So now we first have actually multiplied we've now got a bunch of point sources, the infilled point area in the source. We want to then take that those point source, those infield areas, and subtract them from the original background source. So we're going to have another image map.py. Which takes our mask original fits file and this image math here, it produces an image math multiply.fits, and we want to take, when we take this image math multiply and subtract it from the original masked image, so that we're going to then end up with just a bunch of point sources. So did we do that? Yes. Okay, so we can then again I have to then modify our source reference. We're going to reference the image mask subtract to be that. And now the subtracted source is basically a bunch of point sources all sitting on a bed of zeros. So we can't use the entire image to sort of separately generate the noise. What we have to do in this case is we actually have to feed in a value here for saying what the reference noise is. Now, we're going to say our reference noise is a little bit higher than the actual formal noise because of the following reason. We zoom right in here. We can do that anyway because we're going to select some sources in here. I chose a high value because it looks like the head of this head-tail radio galaxy is very close to this little background point source, which we do not want included in, which will get included in here if we have a lower flux density. So what we want to do now is we can take the three sources here, and we can then say, okay, those are the three we want. Again, they're not a super polygon because they're all separate objects as far as we know. And let's see what these look like here. So we have the information about our head-tail galaxy here. It's about 6 millijanskis. The center source in the cluster is about 2 millijanskis. And our little source, it turns out that through in-painting, we've actually kind of got rid of some of the sort of smearing of the background point source, and our analysis says that actually it's only about it's really a point source, and it's got about 0.3 mil. It's at about the 0.3 Jansky level. So that gives you a little bit of a detail of what's been going on here. Thanks for listening, and see you next time.